We are something chapter 13 sounds good. We'll do chapter 13. Last time we did big ice table Thursday. Yes. We did all kinds of ice table type problems, equilibrium type problems. So as we saw there, there's kind of three ways really that we can solve sort of these equilibrium problems in this class. Again, we could use our quadratic. We also saw, we could have like a perfect square on both sides, which was not bad, that one. We also talked about making an assumption and assuming that x is equal to 0. Remember that when we do that, that is when a situation where we have a small value of k is really the only time that you can sort of make that assumption. And the idea behind that, as we talked about, is that because the k value is relatively small, that means when we reach equilibrium, we should pretty much mainly have reactants present. And that means that when we get to sort of the change part of our table, it's going to be a relatively small number, so almost negligible. And that is, again, why we could assume that. Remember that when you do make the assumption, you do need to check to make sure that the assumption is okay. And what we're going to follow in this class, again, is what's sometimes referred to as the 5% rule. And basically the way that you check it is you take the x value that you got after you made the assumption, you divide it by really the initial concentration, which is sort of what you're going to subtract it from the table. So if you had like 4 molar here at equilibrium, maybe 4 minus x. So in this case, we would divide it by 4 in this case, times it by 100%. And again, if it's sort of less than 5%, then your assumption is okay, and you can use that x value to solve for what you're looking for in the case of most problems, equilibrium concentrations or pressures. If the x value is, again, above 5%, then you do need to go back and sort of solve it another way. And for us, again, that probably would mean you do need to go into your quadratic. You can also just go into the quadratic without using the assumption. If you rather just do the calculation, you could do that too. It should come out the same. Yeah. You can. Yeah, so that's what I was just saying. You can definitely still go into the quadratic and do it that way, and it should get you pretty much the same number. So you definitely could just roll through it, but it can save you some time, especially if you have a small value of k, to make the assumption, but you technically don't have to do the assumption. You can just do it like normal. Other questions on that? As I also mentioned, I think at the very end last time, there's another way to solve these type problems, which again is successive approximation. And again, we won't be doing that in this class, but sometimes in books and stuff like that, they show it sort of solved that way. But we won't do any successive approximation, which again, as I talked about at the end there, basically means that if this is 4, I know my x value has got to be smaller than 4. So you kind of pick a 4 or something less than 4. And you put it in, you keep one x that you solve for. And again, you keep doing that process. You put in the x value, you solve for x until they equal each other. And if they don't, then that x value that you got, you put back in and you keep going until they equal each other. And again, at some point, that could be a very bad, long process if you are not so great at it. Any questions on solving equilibrium problems? Definitely the major calculation for the semester here, and definitely something you need to be able to do. Any questions on any parts of that there? The other thing we talked about as well is, again, when you do go into the ice table, and if you are dealing with something with pressures, once again, it does need to be an atmospheres when it goes into the ice table and do that. So the last thing we're going to talk about then in this chapter is our good friend Le Chatelier's principle. And Le Chatelier's principle is an idea of when we do have an equilibrium, that is a system that is at equilibrium, we basically do something to, frankly, screw it up, and it's no longer at equilibrium. So in Le Chatelier's principle, we have this nice system. It's at equilibrium. And what we do is we add a stress to it. And a stress can be something to do with the concentration. Maybe we add or remove something. It could deal with the pressure or volume if you're dealing with some type of gas equilibrium. It could also deal with the temperature. Again, either kind of increase or decrease the temperature. And also a catalyst, possibly. So when we have a system that's at equilibrium, which as we've talked about means that the rate of the forward direction will equal our rate of our reverse direction. We do something to it. Again, we maybe play with concentration, volumes, pressures, temperatures. And what that does is it basically kind of messes up the equilibrium. And this system will want to basically readjust itself to once again get back to an equilibrium sort of state. So we have a system at equilibrium, we do something to it, it screws it up, and it wants to get back to that equilibrium state. And there's really sort of three options that could happen. It sometimes what is referred to as shifting to the right, which basically means it needs to make more products. It could shift to the left, which means in order to reach equilibrium, it needs to make more reactants. And there's also some situations that no matter sort of what you did to it, even though you did something to it, it actually could have actually no effect or no change on the equilibrium. So it won't really shift one way or the other. And what will eventually happen is we have this system sort of at equilibrium. We do something to it here to mess it up by adding a stress. It reacts by shifting one way or the other. And what ends up happening is this reaction will once again return to equilibrium. Step there, yeah. So that's sort of the process of Le Chatelier's principle. And we could use the Chatleir's principle to our benefit in a lot of cases to force reactions one way or the other. For example, if you wanted to a reaction to go to product side or a reactant side, you could do something to it to sort of force it to do that by taking advantage of sort of Le Chatelier's principle. Any questions on that there? All right. I guess that's kind of like 2A, I guess, or do something to it. All right, so let's talk about each of these individually here. So I'm just going to kind of freehand it here, a little concentration action here. So obviously with concentration, there's really two things that we could do. We could add more, and we could add more reactants or more products. And when we add more, it will shift away from the side that was added. So AA, add away. Yes, it goes away from the side that you added. And number two there is the other thing we could do is remove. And when we remove concentration, we shift towards the side. So if we have a system that is at equilibrium, for example, here, represented by award-winning drawn stick figures. This is advanced stick figures. They have faces. You don't get that in intro to stick figures. You just get the body and the head, no faces. That's good. So if this guy on the left here is our reactants, this guy over here represents our products. And in this particular case, if, for example, somebody hopped on to this side here, what's going to happen is, again, we're at equilibrium here. we will have our guys that are on this side having fun. This guy, maybe not so much fun in this case. Yeah. Obviously, we added more there to the right-hand side, messed up the equilibrium. Now to fix this right, we need to put more people on the right, more people on the left. Which way? Yeah, so we added to the right. We're going to shift away from the side we added it to. We need to put more people there on the left-hand side. And once again, this system can come back to equilibrium. And we're breast here back at equilibrium number 2 position, number 1 position in this case. So in this case, we added more products, it shifted away from it. And the real reason is when we add more products, that's going to cause which reaction to actually occur? The reverse reaction, right? There's going to be an abundance of products there. So that's going to allow the products to react a lot more easily than the reactants. And that's going to kick off the reverse reaction, in this case, basically to occur. Now, if we again have our equilibrium here set up, and once again, the guy on the left there's our reactants, guy on the right is our products, and this guy decides I've had enough. I'm going to hop off the ride here. We're going to get this situation here. In this case, to fix this here, we need to put more people which way? Yeah, we need to go to the right-hand side, right, to basically towards the side where we removed it from. This will return this reaction back to equilibrium in this case. Everybody's happy, and clearly the take-home message is do not be on this side. Seems like the bad side of this seesaw here. So again, the sort of same idea is in play here. When I remove my products, the only stuff that's sort of available is a lot more reactants, right? Which is going to kick off the forward direction basically happening in this case. So the same sort of thing happens, obviously, if we added more reactants. If we added more reactants, we would have a lot more reactants, which would also kick off the forward reaction and cause it to shift towards the products. And if we removed reactants, that would mean that we have more products, which would cause, again, an influx in the reverse reaction happening. So add away, when you remove it goes towards it. Any questions on that? So let's also talk about what happens when we have our friend pressure and volume. Pressure and volume usually makes me think about gases. And when I think about pressure and volume, there's that guy, I think it was Boyle, perhaps. Yes. He had a gas law. The relationship between pressure and volume is what? As the pressure goes up, what happens to the volume? Volume goes down, right? Volume goes down, a lot more collisions, right? More collisions means more pressure, and vice versa, right? As the pressure goes down, volume will typically go up in this case. So we start to see, obviously, the pressure start to drop as the gas molecules have a lot more room to fly around. So in this situation, when we're dealing with pressures, as the pressure goes up, volume will go down. And the change that we're kind of seeing here is basically the pressure starting to go up. So we want to counteract that by kind of bringing the pressure back down. But because the volume is now much smaller, the only way to bring down pressure in a small volume is to have more or less gas molecules. Less is right, I think, as you whispered that. Yes, less is right in that case. Less gas molecules in a smaller volume means it's going to take longer, right, for collisions to occur. More gas molecules would mean we would still see the pressure continue to go up, right? So what's going to happen in this case, because the pressure is starting to sort of go up to sort of counteract it and bring it back down, we're going to shift to the side with the least number of gas molecules. And that obviously is reaction dependent onto which side has the least number of gas molecules. And if you have an equation to figure out how many gas molecules you have, is you just add up the coefficients for anything that's got a G next to it, right? And that will tell you how many gas molecules there are on either side of the arrow. And the opposite is sort of true here as the pressure starts to go down because the volume went up. So it's sort of the same idea. The change that we're sort of seeing happening here is the pressure is starting to come down. So we kind of want to bring it back up a little bit, but now we have a larger volume. So again, in that larger volume, we would actually need to fill it with a lot more gas molecules to kind of increase the number of collisions that would occur, and that would sort of bring the pressure back up. So in this case, larger volume, more gas molecules. So we'll shift to the side with the most gas molecules. So this one, you could remember, or you could think of it in terms of volume. Small volume, less gas molecules. Larger volume, more gas molecules. And again, it is reaction dependent as to which side that would be. So for example, if I had something like 2A plus B goes to 4C. All right, and let's see what will happen in this case. Let's say we added more C, we removed B, we increased the pressure, we increased the volume. All right, will it shift to the right? Will it shift to the left, or will there be no change? So take a second there and decide what will happen in each of these cases. And why don't we add A as well? Okay, let's take a look. So we're going to add more C. So C is a product, which means basically that should go away from it. So it should shift to the left there. Again, because we're going to have more products, that's going to increase the reverse reaction in this case. Any questions on that one there? If we remove B, you could kind of think of it, there's now like a hole there on the left-hand side of the equation. We need to fill that hole, right? So it's actually going to go towards it. Also because there's going to be more products than reactants there, and that's going to also kick off really the reverse reaction in that particular case. If we increase the pressure, that means that we should see a decrease in the number, a decrease in the volume. And in a smaller volume, we would need less gas molecules. So on the reactant side, there are 2 gas molecules plus 1, which is 3 gas molecules, just adding the coefficients. Anything that has a G obviously next to it. And over here, that's a gas, and there's a 4, so that has 4 gas molecules. So in this particular case, it would shift to the left as well. Any questions on that? Again, in a smaller volume, we would need less gas molecules to sort of bring the pressure sort of back down, and it'll be less collisions. If we increase the volume, again, that means that we have more space, and we would then if they have the same amount, there would be no side that's more or less, so that then would mean no change. So that's a situation where you could get no change is when you're comparing the gas molecules on both sides, they're the same, basically. Other questions? All right, so increasing the volume, that means that we have more room for everybody to fly around. That's why the pressure is dropping. So to kind of bring the pressure back up, we need more gas molecules to fill it. And in this case, that means it needs to go to the right. And lastly here, if we add more A, we're going to have more reactants to react, which means it should shift to the right. Any questions on that? Now, by the way, when we talk about sort of right and left, right, I say right 3 times in that sentence there. So there is no left-hand side and right-hand side of the beaker, right? They're all floating around in there. So, all of our stuff is floating around in that beaker. So when we talk about right and left, obviously we're talking about the equation and, left-hand side, right-hand side of the equation. Any questions on that stuff there? All right, the next sort of stress that can affect it is temperature. So temperature is the next guy that can affect the equilibrium. And basically, when we talk about temperature, there's really two types of processes that come about with that. And that, again, is a exothermic process where energy is released, and endothermic process where energy is absorbed. And the most common way that we sort of see temperature or energy sort of displayed really in an equation, really more energy, is through delta H, which again is our enthalpy. And we probably have talked about this previously, but again, if you see a negative value for delta H, that's going to mean that it's an exothermic reaction. If you see a positive value for H, that's going to mean that it's endothermic. So when we think about exothermic and endothermic in terms of reactions, our equations, we think about them as being on sort of opposite sides. So something with an exothermic sort of process, we think of heat and energy as a product. Not 100% correct, but that's how we sort of do it. So we think of it here as a product. When we're dealing with a endothermic reaction, we think of heat and energy as a reactant. So that's really important because basically temperature works the same as concentration, which means that if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards. Now, away and towards is dependent again on exothermic or endothermic as to which way you would see that. So if you increase the temperature of an exothermic reaction, it'll be like adding more products, and we would expect it to go towards the reactant side. If you increase the temperature of an endothermic process, it means that it's like adding more reactants, and we would expect it to shift away. If you throw everything on ice, in an exothermic reaction, it'll be like removing products. So we would expect the reaction to shift towards the product side. So when you're dealing with sort of temperature, the first thing you want to determine is it exothermic or endothermic? And again, it treats the same as concentration. If you add, it goes away. And if you remove, it goes towards. The other thing about temperature that we talked about again is it is the only thing that has an effect on the value of K. So once again, the K at say 27 degrees Celsius versus 40 degrees Celsius, these K values will be different. But also, as we talked about earlier, that if you did a bunch of experiments at 27 degrees Celsius and left it at 27 degrees Celsius, all the K values should be the same. And if you did a bunch of reactions at 40 degrees Celsius, different experiments, they all should be about the same. But in comparing the K value at 27 to 40, those values should be different and stuff like that. So temperature, once again, is the only thing that affects the actual value of the equilibrium constant. Any questions on temperature there? Now, the last thing that can sort of maybe affect it, but not really, is a catalyst. And as we talked about before, a catalyst is, again, not a reactant. It is not a product. It does not get used up in a reaction. It's basically there to sort of facilitate the reaction occurring faster. And as we talked about, by lowering that activation energy, finding an alternative pathway for it to do it. In terms of Le Chatelier's principle, adding a catalyst will have no effect. So no change will occur when you add a catalyst. Same thing, for example, if you added like a noble gas. Noble gases are chemically inert, so it will have no effect on it as well. So those are a couple of ways that you can get a no change. And as the question was asked earlier, the other common way that you can get no change again is in the gas sort of comparison. You have the same number of gas molecules on each side. Any questions on Le Chatelier's principle there? Let's take a look at some of this stuff here, maybe that you got on your notes there. So this is what we talked about. Again, concentration shifts away and goes towards whatever you removed. Temperature works the same way. And again, it's the only thing that would affect it. And our pressure and volume, which is usually tied together in a lot of cases. So we'll take this guy here and we'll just say, for the sake of argument, this is not the correct value at all, but we'll go with this negative 125 kilojoules, the delta H. Again, definitely not the right one. All right, so I want to know what will happen in this situation if I remove H2, I increase actually, let me do this. I decrease the volume. I lower the temperature. I add some N2. I remove NH3. I decrease the pressure. I increase temperature. I add a catalyst. All right, so again, we'll go to the right, we'll go to the left, or will there be no change in this case for each of those things based on my made up delta H value? All right, let's take a look. We're going to remove H2 here. We're going to remove our reactants. Again, kind of like a hole on this side. So it's going to go towards it to fill it. So it should go to the left. We got our decrease in volume, which means our pressure goes up. And with a smaller volume, we need less gas molecules. And in this case, we got 4 gas molecules on this side and 2 on this side. Once again, the coefficients is how we get there. So that means that we are going to shift in this case to the right as we will need less gas molecules. Lowering the temperature, we see in my made up delta H, that's negative, which implies that this is going to be exothermic. That also implies that heat would basically be a product. So if I lower the temperature at this point, it's like removing the products, and then it would then go towards the product side in that case. Yes, any questions on that there? Adding N2. N2 is a reactant. That should kick off really the forward direction from happening. And then that would shift away from it. Removing NH3, which is a product. So again, it creates like a hole on the product side. And it's going to go towards the product side there to fill that hole, if you want to think about it that way. Decreasing the pressure means that my volume should go up. And that means a larger volume would need more gas molecules, basically, to kind of bring the pressure back up. And that, in this case, would shift to the left. Increase in the temperature. So once again here, exothermic reaction, increasing the temperature because it's on the product side would be like adding more products. And that essentially would kick off the reverse reaction happening. And we would see it go away from that side. And lastly here, adding a catalyst would give us no change. Any questions on any of those shifts? Yeah. Okay. All right, this last one you got, I think. And I think maybe the 2 is missing on your handout, so you might want to add it there. So we'll try this one here. Let's do we'll add some NO. We will increase the temperature. We will decrease the volume. We will add some O2. We will do something else maybe. We'll remove some N2. And we will decrease the pressure. All right, which ways you can go? Right, left, no change. The one on Canvas, the slides are up on Canvas. Yes, do we not know that? No. So, you know, all the lecture notes are up on Canvas, just so you know. Yes. Wait, look at Canvas. Nobody looks at Canvas. That's how you learn more writing by hand. That's good. That's all right. It's under the section that says lecture notes. All right, let's take a look at this here. So we're adding more NO, which is our product. So again, that's going to kick off our reverse reaction. So again, it will shift away from it. In this case, we're going to increase the temperature. It's endothermic. So that means that heat will be acting as a reactant. And in this case, when we increase in it, we're basically increasing our reactant side, which should kick off the forward reaction happening in this case. As we decrease the volume here, that means that the pressure should increase. And to bring back down the pressure, we would want to go to the side that has the least number of gas molecules. In this case, which side is that? Neither. They both have 2 gas molecules. So that would be a no change in this situation. Because of that, we will add O2. So once again, we're adding more reactants, which is going to cause that forward reaction to occur because of the presence of all those reactants, and it should again shift away from the side we added it from. We're going to remove N2, which is a reactant. So that's going to make like a hole over there on the reactant side. And in reality, that means we have more products really. So that's going to cause the reverse reaction to go towards it to kind of fill in that hole. And here we're going to decrease the pressure, which means that the volume increases. And once again, here, since we have the same number of gas molecules, which is 2 gas molecules on both sides, we will again get a no change in the situation. Any questions on that there? Questions on Le Chatelier's principle? All right, that wraps up chapter 13. Yes, good deal. All right, we're going to talk about acid and bases here. And again, like I said, this is getting into 14 and 15 in exam 2 material, really the part where a lot of people do struggle. It is a lot of conceptual understanding of what's going on so that you could do the math. The math is sort of based on sort of what we talked about with some variations of that calculation, but it's really critical to understand what is happening in these problems so that you can sort of do the math correctly. So the first part of chapter 14, which is a very long chapter, is a lot of stuff in there, is basic acid and bases. So we'll just talk about those guys there. As my acids is hiding behind my orange here. There we go. All right. So acids, they have a sour taste. So for example, vinegar is acetic acid. Citric fruits have citric acid. They react with certain metals to produce hydrogen gas, that you may be aware of. Like if we take some zinc and a little hydrochloric acid, the zinc comes in and kicks out the hydrogen, creating zinc chloride and a little hydrogen gas action, right? And maybe a little balancing, like I'm a chemistry instructor there. There we go. This is a single replacement reaction, right? Whatever's coming in needs to be more reactive than what it's replacing. They react with carbonates and bicarbonates to produce carbon dioxide gas. So for example, if you took a little hydrochloric acid plus a little sodium carbonate, it's going to do a double displacement reaction, right? We're going to switch partners right there. and that's going to form H2CO3, which is carbonic acid, plus a little sodium chloride. A little 2 there as well. This, as you might know, is something that will go through a decomposition reaction really quickly and produce our CO2 and some water in this case. So that is where our CO2 comes from. The formation basically of a acid here, a weak acid that will sort of break apart and make CO2 gas. Speaking of our friends acids, let's talk a little bit about, just to make sure everybody's on the same page, a little bit of naming acids, right? So you don't say this thing, right, to name. So as you, I'm sure, remember, when you go to name acids, it's all about oxygen, right? And if there is no oxygen, the acid name is hydro something ic acid, right? So like HCl, no oxygen, so that's hydro. The middle part there is the anion in this case, and that would be hydrochloric acid. We have something like HBr, that is hydrobromic acid. By the way, the cation for all acids is the H plus, right? So the H plus is the cation in each of these cases. By the way, we put AQ, which is aqueous, next to acids because if this was HCl with a G, this would be called hydrogen chloride. Yeah, so acids are substances that basically can release an H plus in solution, which is why acids always have the aqueous symbol next to it, because they should be solutions in this case, right? So this would be hydrogen chloride gas, which, if you take and bubble it through water, then you get hydrochloric acid. Now, if it does have oxygen, it will contain one of those polyatomic ions that everybody loves. And as you remember, those polyatomic ions end in ate or ite, right? So if your polyatomic ion ends in ate, your acid will be something ic acid, like HNO3. That is nitrate, which means this is nitric acid. H2SO4, that is sulfate, that is sulfuric acid, right? And if your polyatomic ion ends in ite, your acid name will be OUS acid. So like HNO2, that is nitrite, that is nitrous acid. H2SO3, sulfite, sulfurous acid. Yeah. Any questions on hopefully review of naming acids? That sounds sort of familiar, I hope. Yeah. So again, hydro only for ones that do not contain oxygen. Ones that do contain oxygens are sometimes referred to as oxyacids because they do contain oxygens in there. And they usually will have, if they do have oxygen, they'll usually have that OH bond, and that is the hydrogen that comes off that makes it an acid, one of those oxyacids. Any questions on naming? All right, then now you won't say that thing there. That's going to burn my hand is off. All right, so now we'll talk about bases here. Bases do feel very slippery. Many soaps contain bases. A lot of our bases and a lot of our strong bases come from group 1 and 2 on the periodic table. Group 1 is the alkali metals, right? Group 2 is the alkaline earth metals. The word alkaline means basic. That's what it means. So that is where a lot of our strong bases come from. Group 1, group 2 on the periodic table. I'll throw a little hydroxide on there. and you have some bases that happen in this case. Things like drain cleaner and those type of things are bases. You can go to Home Depot and get just straight sodium hydroxide to clean your drain instead of Drano or whatever they use there. All right, so when we talk about acids, a basic definition of acid is one done by Uranus, and that is a substance that can produce H plus ions in solution. And it is free H plus, that is the hydrogen ion. And H3O plus is what is known as the hydronium ion, and that is a polyatomic ion. And in acid-base chemistry, H plus and H3O plus are used interchangeably. Yeah. So you can use H plus in formulas. You could also use H plus in equations, and you could use H3O plus in formulas and equations. I personally, most of the time, will use H plus. So anywhere I put in H plus, you could pretty much put in H3O plus, and it's going to mean pretty much the same thing. There is a reason why you get H plus versus H3O plus, and it's really how you write the reaction or the equation. So for example, this is really hydrochloric acid just simply going into solution and breaking apart. And this is perfectly fine way to write it. When you include the water, we get the H3O plus. You can just as simply, in this case, write this equation as hydrochloric acid breaks apart into H plus and Cl minus. Again, here I didn't include the water on the reactant side, so I did not produce H3O plus, but they are equivalent. So this H plus here and this H3O plus here are basically equivalent to each other. So if you include the water in your equation, you should probably get H3O plus on the product side. We'll talk why that is in a second. And if you do not include the water, you should just probably get H plus on the other side. Bases, on the other hand, are substances that have the ability to produce OH minus in solution. Not all bases will have hydroxide on board, if you will. Some of them has to go through a little reaction to produce hydroxide. So ammonia is actually, as we'll talk about, a weak base. But because it's able to produce hydroxide in solution, it is considered still a base. So here's the deal. If you got a solution or a beaker and you got H plus or H3O plus floating around, it's going to probably, be more of an acid. If you got free OH minus floating around, you're going to have a basic component to it. And again, when we talk about being an acid or base, is the ability to produce those things free from anything else, just free floating in there. And the amount of H plus versus the amount of OH minus will tell you whether or not a solution will be acidic or basic overall. But these guys are able to release those things. And in the case of an acid, basically something like HCl, it's that H that comes off, and any type of oxy acid, it's that H that's attached to that O. That's basically what comes off in solution. Now, Arrhenius did a lot of work with really strong bases, and a more sort of general definition of an acid and base is the one done by Bronsted and Lowry. Not sure why he got cut off here, but we'll add his name back. So the Bronsted-Lowry definition of an acid is a proton donor. That is something that gives away a proton. And by the way, a proton is H plus. Yeah. We call it a proton because hydrogen has how many protons? How many electrons? How many neutrons? 0. So in order to become positively charged, you have to lose your electron, which leaves it just a proton. Yeah, so that is why H plus is referred to as a proton in this case. So something that's able to give away an H and the plus, which is also really important because that will change the charge, is a Bronsted-Lowry acid. Bronsted-Lowry base is somebody that will accept the H plus. And also that will affect it. So in the case of our NH3, this is a base. The water here is acting as the acid. And in this case, the water is going to send the H plus over to the NH3. The result of that is we will make NH3, NH4 plus over here. And when water loses the H plus, it becomes OH minus. And that is our obviously formation of our hydroxide, which is why it's a base. The consequences of the Bronsted Lowry definition is it will create pairs on opposite sides of the arrow. So the base on the left-hand side is paired up with what is known as the conjugate acid on the left-hand side, right-hand side of the arrow. On the left-hand side of the arrow, the acid is paired up with the conjugate base in this case. Now, the only difference between an acid and its conjugate base partner are a base and its conjugate acid partner is this guy right here. It is the only thing that can be different. It is one H plus difference. So when we look at the base to the acid, it has one more H plus than it started with. And when we go from the acid to the conjugate base, it has one less H plus. And that is because, again, the acid is giving away that H plus. So in order for these guys to be pairs, our base pairs, it can only be a difference of one H plus only. That is also why when we look at our HCl that we saw earlier, when we do include the water in this reaction, this is our acid. Water in this case is acting as a base for the acid, and the acid's going to donate the H plus over. And when it does so, we will end up with Cl minus and our H3O plus that we saw earlier. And that is why we do end up with H3O plus when we include water in there. And in this case, this is our acid. This would be our conjugate base. This would be our base, and this would be our conjugate acid. And once again, the only difference is the 1H plus difference. So this is why in the case of something like hydrochloric acid, which is actually a strong acid, it will, when it goes for a swim, pretty much 100% break apart into its ions. And you can show that by including water in the equation. But again, you don't need to. You could just simply show that like we did earlier there of the HCl, break it apart into H plus and Cl minus. So this is why in some cases you may see the H3O plus and you may not see it in other cases. I would say very commonly, books will probably include the water even with acids. They're really not reacting with anything. It's just kind of breaking apart in water, basically dissociating. But you should definitely probably include the water when you're writing the reactions for bases because it helps you visualize maybe where everybody's coming from and where the H plus is going and stuff like that. So once again, these are Bronsted Lowry acid conjugate base pairs. The absolutely only difference between something that's considered a pair has to be one H plus, and if it's anything more than that, then they are not considered pairs. Any questions? All right, so for each of these on this list, decide, are these conjugate acid base pairs? Take a look and see what you come up with. Okay, let's take a look. So is the first one a pair? First one is differences in H plus, but there's also a difference of an oxygen, which means not so much. Yeah, so that would definitely not be a pair because of that. How about second one? Second one, pair? Difference between these two is two hydrogens, which means not a pair. Yeah, even though they are related, but they are not related in that sense of being a pair because it is actually more than one hydrogen that is difference. How about the next one here? Yeah, so this one again is a difference really of just one hydrogen, so I'm gonna go with that. It's good. How about our H3O plus and our OH minus? Now that's a couple of hydrogens difference. So I'm assuming none of those would not be the right answer either. So I'm gonna go with 3. That looks like the only one here. Questions on that? So it's a really important idea as well to understand that hydrogens, when they come off for an acid, for example, something like our friend here, sulfuric acid. Sulfuric acid is what is referred to as a diprotic acid, right? And diprotic means it has 2 hydrogens that can come off. Monoprotic means that it has 1 hydrogen, right? And you could have triprotic, which is like 3 hydrogens, right? Like phosphoric acid, for example. They actually do come off one at a time. So it is actually a stepwise sort of process as to how they come off. So the first thing that would happen is, for example, we would lose 1 H plus, and then we would have HSO4 minus. Then our HSO4 minus will lose another hydrogen and become SO4 2 minus, right? So when we look at this, the things that are pairs, as I blank the screen for dramatic purposes, this guy and this guy, right? The difference here is 1 H plus, and they would be partners. This guy on the second equation and our sulfate here would be partners as well. But going from the beginning to the very end there is a 2-jump process, and they would not be partners in that case. We sometimes think of this as the overall reaction, right? That's how we get there, by the way. This cancels, that cancels, and we're left with H2SO4, gives you 2 hydrogens and a sulfate, which is most of probably what you dealt with in Chem 50 is the overall reaction. But anything that is diprotic or triprotic, those hydrogens will actually come off one step at a time, which is why, again, although obviously H2SO4 and SO4 2 minus are related to each other, they are not considered pairs because, again, it's kind of 2 steps down the road from each other in terms of where they started from. Any questions on that? Yeah. By the way, as well, what we saw here, for example, in both of these reactions, we also saw that water in the first case acted as a acid, right? And in the second case, it acted as a base. And there are certain things that could act either as an acid or a base. And those things are what are referred to as being amphoteric. Is a substance that can act as an acid or a base. And water's a prime example of that. That's actually what happens when water is with itself. Some waters act as acids, other waters act as base as they react with each other. Very commonly as well, something like we just saw there, for example, that has an H and S and O4, like an H and a minus can go both ways. It can gain a hydrogen and become like sulfuric acid, can lose a hydrogen and become sulfate. So again, it can act as an acid or base because it has the hydrogen and it's able to basically do that. So there are certain things that can go one way or the other. And some of the challenges in this chapter is at certain times you'll have to decide which way it's going. And there are things that you have to look at as you start to make that decision. And we'll talk about what you should look at when we do. Yes. That's hydrogen sulfate. Or bisulfate is sometimes referred to. It's kind of like bicarbonate or hydrogen carbonate. Same with it, yeah. Other questions? All right, let's try another one here. We have something C6H5NH2. What would be the formula of the conjugate acid for this guy? Okay, so let's take a look. So again, they were nice enough to tell you what it is, but sometimes they do not. So if we think about sort of our relationship On one side, we have the acid, and its partner on the other side is conjugate base. And on one side, we have the base and its partner is conjugate acid. By the way, that is typically how it is usually done. Regular old acid and base is on the left-hand side of the arrow, your conjugate partners on the right-hand side of the arrow there. So in this particular case, we're looking for the conjugate acid. So if they did not tell you that was a base, you could kind of think about it backwards and you would know that what you're looking at is a base. You should hopefully know that the only thing you need to do is an H plus, either put it on or take it off. And that's kind of the hard part sometimes. So in this case, the definition of a base is something that will accept the H plus. So we actually want to put on the H plus in this case. So that means we have C6H5 NH3 plus in this case. 2, it looks like maybe there would be the right choice. Question on that one. Yeah.
Shouldn't it be the other way? We're trying to lose one because it's the base going to an acid.
No, because the base itself is actually something that accepts it. So as you go from this direction, from the base to the conjugate acid, there's actually one more H plus in that case, because the base itself is the one that accepts it. So once it accepts it, it becomes a conjugated acid and thus has one more H plus than before. Yeah. It doesn't really matter where you put it. I just put it at the end. You could put the H at the beginning. As long as you put an extra H in there and a plus, then you should be good. This case, yeah. So you do need the plus, right? Because again, it's not just an H, which is a common mistake. That plus obviously affects the overall charge. So you got to make sure that you include it in there. So I want to try one more here. Let's say we had our bicarbonate, which was we talked about there a second ago. Let's write the formula for the conjugate acid and also the conjugate base, starting in both cases with this guy. Okay, so we'll start with the conjugate acid we want to write. So once again, if we want to end up over here, we know backwards thinking that in this case is going to act as a base. And again, the Bronsted Lowry definition is, again, it should accept the H plus. So this would end up as H2CO3, as we should be adding the H plus. Obviously, by default here is probably the opposite, but we could think about it oppositely here. If we're starting with our conjugate base, once again, its partner on the other side is an acid. And an acid is something that will donate an H plus. So what we're looking at is something that will actually give away the H plus. So it will subtract the H plus as we go that way. So when we lose the H, we're left with CO3. And again, when we lose a positive, we become one more negative, right? So we make some carbonate in this case. Any questions on how to write acid conjugate base pairs? You obviously need to be able to do that. Any questions on that?